Welcome to calculus. You will master complex problems, but forget how to add. On this episode, Stevenson will demonstrate Now let's look at another example and ultimately then vertical asymptotes after that. But let's look at this example here. This is another illustration of applying the properties, those limit properties with infinity and squeeze theorem. So I want the limit of 5x plus sine of x all over x as x approaches positive infinity. So the first step is to break up our fraction as such. So this is that method I showed you in the previous video. So I simplify, x divided by x is 5 and sine of x over x. Now I would take the limit of each one individually. So the limit of the entire function is really equal to the limit of the first piece plus the limit of the second. That's the limit properties, right? The limit of a sum is just the sum of the limits. So the limit of 5 as x approaches infinity is just 5 because 5 is constant. So if you were to graph it, it would just be a horizontal line at 5. Super boring. Now, the limit as x approaches a positive infinity of sine of x over x is 0. And the reason for that is because in example 2, we were actually able to, prove that using squeeze theorem, okay, in that example there. So thus, you're really just doing 5 plus 0, which is 5. Now, we talked about horizontal asymptotes, so let's look at vertical asymptotes. So if the values of a function outgrow all positive bounds as x approaches a finite number, then we say the limit of f of x as x approaches a equals positive infinity. If the values of f become large and negative, exceeding all negative bounds as x approaches a, then we say the limit of f of x as x approaches a equals negative infinity. So if we look back at our graph of 1 over x, we can observe that the limit of our function 1 over x as x approaches 0 from the right. So if we approach 0 from this side right here, we can see the limit is going to be positive infinity. If we approach the limit from 0, or as x approaches 0 from the left, we can see the limit is going to be negative infinity. So ultimately what we can now conclude is this y-axis, or the line x equals 0, is a vertical asymptote. So just like with horizontal asymptotes, we understand vertical asymptotes, but now what we can do is define them using limit notation. So by definition, the line x equals a is considered a vertical asymptote of the graph of a function y equals f of x if either the limit of f of x as x approaches a from the right is either positive or negative infinity, or the limit of f of x as x approaches a from the left equals plus or minus infinity. So in other words, if you take the limit of a function and x is approaching a number and the result is infinity, whether it's positive or negative, that tells you that number is a vertical asymptote. So let's look at example 4 here. So it says find the vertical asymptotes of the graph f of x equals 1 over x squared. It says describe the behavior to the right and the left of each vertical asymptote. So remember what that looks like. We want the limit as of either side of x equals 0 because x equals 0 is the vertical asymptote. Okay, so if I approach 0 from the right, then I can see my function is approaching positive infinity. If I approach 0 from the left, I can see my function is also approaching positive infinity. By the way, it doesn't matter that these match. What matters is that the result is an infinity, therefore we know it is a vertical asymptote. Okay, and actually in this case, it's the only vertical asymptote. So let's look at 27. 27 is a set of problems where it says A, find the vertical asymptote of the graph of f of x, and then B, describe the behavior of the f of x to the left and the right of each vertical asymptote. So this should look very familiar. Let's factor it. So first of all, what are the vertical asymptotes going to be? Now what we need to do, now 27 allows us to use a calculator, which is fine. It says to describe the behavior to the left and right of each of those vertical asymptotes. So let's start with x equals negative 2. As x approaches negative 2 from the left, of f of x, don't waste your time writing out the full function. Just use its function name. It'll be so much simpler. So the limit as x approaches negative 2 from the left, we can see is going to be positive infinity. The limit as x approaches negative 2 from the right, I'm misspeaking, the limit of f of x as x approaches negative 2 from the right is going to be negative infinity. The limit of f of x as x approaches positive 2 from the left is negative infinity. And the limit of f of x as x approaches positive 2 from the right, so this is positive 2 from the right, is positive infinity. So, whoops, you can't see all that. So there you go. Be very careful of your notation. Make sure the LIM and your f of x is on the same level, and then what x is approaching is below it. Okay, so be very proper and careful and be mindful of your notation.